Okay, so I'll first start off with a common answer that I got in the problem set homeworks. And it's a good start to the problem, but it wasn't followed all the way through. And that came from not really justifying why the answer actually gave you the smallest integer n. So what a lot of people did was they first converted everything to fraction form so that things would be easier to compare. So 33% is just 33 on 100, less than m on n, less than a third. And so the first thing that people did was just try and get a common denominator. So again, we can compare everything. And the lowest common multiple of 103 is 300. So we're just going to make everything have a denominator of 300. But I'm not going to change this m on n. I just want the outsides to be comparable. So we get 99 on 300. And on this side, we get 100 on 300. So a lot of students at this point realized that if n was to be 300, then there is no integer m which makes this work, because there's no integer that's strictly between 99 and 100. So that means that n can't be 300. And the next thing that people did was actually go all the way to 600. So I guess I'm not exactly sure how that happens, but a lot of students thought, okay, let's just try and increase the denominator by a factor of 2, because surely then the gap between these numerators will become big enough that I can squeeze an integer inside that. So I can squeeze an integer m inside those numbers. And so they did 198 on 600, less than m on n, less than 200 on 600. So I guess that's where the temptation to multiply the top and bottom by 2 came from, because I think a lot of students recognized that there was a gap of 1 between these numbers. So there was no way to fit m inside it. And I think it was easy for people to then go, okay, if I want to fit an integer between 2 integers, then I need that gap to be of size 2. Gap of size 2. But that's not necessarily the case. So, like, of course, if you've got integers on the number line, then 198 and 200 is promising, because then you can just select m to be this value here, right? Okay, so what happened here was, if n was equal to 600, then we know that m can equal 199, because that's between 198 and 200. So that means that n is an upper bound to our solution, because we're trying to look for the smallest integer n. And since we know that 600 works, so n equals 600 works, then we know our answer has to be 600 or smaller if there exists a smaller solution. And yeah, indeed, if n is equal to 600, then we just need to choose our numerator to be between the 2 numerators on the outside. And it feels like this is the smallest we can go, because it felt like the gap of size 2 was the smallest gap you could get that allows this thing to happen where you can squeeze an integer inside. But the mistake was that a gap of size 2 is not the smallest gap that you can get. And what I mean, and also people didn't even justify this when they gave the answer. People just sort of skipped from 300 to 600 and said that 600 was the answer, without actually justifying why that was the smallest such n. But I'm guessing that this is what people thought. They thought that the gap of size 2 was the smallest you could go. But just as an example, I mean, what if we had a situation where the numerator on the left was not an integer and it lied around here somewhere? So pretend that this number on the left was actually around here and not an integer. And then this number on the right was somewhere around here and not an integer. Well, it's still possible to fit an integer between those. So all we need is that the gap covers an integer. So we only need gap to cover an integer. So that's just another way of saying I want to be able to squeeze an integer between these two values. Okay, and obviously this gap is smaller than 2. So just as a really concrete example to prove why 600 is not actually the smallest, well, let's try n equals 400 and just see what happens. And I'll show you that this gives you an integer value m. So that means if n is 400, then if I try and convert everything to denominator 400, then what do I need to do to figure out what goes in the numerators here? Okay, well here on the left, I had 33 on 100, right? And on the right, I had 100 on 300. So if I want to turn that into a denominator of 400, I need to multiply the bottom by 4, which means I multiply the top by 4. And so what's 33 times 4? Hang on, is this right? Okay, so 33 times 4 is 120 plus 12, which is 132. So I get 132 on 400 on the left. Anyway, and on the right, I get, so on the right, what did I have before? I had 1/3. I don't know why I wrote 100 on 300. Let's just go with 1/3, right? So we had a third on the right and we want to convert that into a denominator of 400. And in order to do that, well, I needed to multiply the bottom by 400 on 3, which means the top is 400 on 3 multiplied by 403. Because 3 times 400 on 3 gives me the 400 on the denominator. And that means I need my top to be 403. I'm going to turn this into a mixed numeral so that we can see exactly what's happening with whole numbers and stuff. So I know that well, basically this is going to be 133 plus 1/3. And how did I get that? Well, 3 times 100 is 300. And then 3 times 33 is 99. So that's 399, which leaves a remainder of 1 on 3. So that's, yeah, plus 1. But yeah, anyway, so it's 133 plus 1/3. Okay. And clearly the integer that we can choose between these two values is 133. So that means that if n is equal to 400, then 133 can be chosen as m. And this is already smaller than 600. And so that's why the solution above is not right. Okay, so that means 400 actually works. 600 works. So that means 400 is an upper bound. But I just randomly showed you 400 to prove a point, just to show that you can make the outside numerators not integers and still be able to squeeze an integer between these. So in order to fully answer this question and be absolutely sure of what the smallest possible value is, let's just go through some cases and see what happens. So I think what I mentioned about this idea of a gap should help us think about the problem, because what we're trying to do is we just need the gap to cover an integer. And so the way that this gap grows and the way that it moves along the number line is going to help us answer the question of what the smallest value of n is. Okay, so we're just going to do some investigation now. And I've already done 400, I've done 600. So what the question gives us is 0.33 less than m on n, less than 1/3, right? So for some reason, I thought it was a good place to start. Since this is a 3, for some reason, I thought it would be a good place to begin with n equals 4. So let's just do that. It doesn't really matter where you start. All we're trying to do is find a pattern and see what happens to the gaps. So if we have n equals 4, then what am I trying to do? I'm trying to see if there is an integer value of m that we can squeeze between these numerators. So what's the numerator here? Well, this fraction on the left is supposed to be the same as 33 on 100. So if I'm trying to get a denominator of 4, then I multiply the denominator by 4 on 100, which means I have to also multiply numerator by 4 on 100. And so what is 33 times 4? It was 132, right? So then that means the numerator becomes 132 on 100. And I'm going to turn that into a mixed thing. So I get 100 on 100 plus 32 on 100. So that's just 1 plus 32 on 100. Okay, great. And what do I get on the right? So on the right, I went from, so I need this to be equal to 1/3, right? And what I did to get a denominator of 4 was multiply the bottom by 4 on 3, which means I have to multiply the top by 4 on 3. And that's obviously just 1 plus 1/3. Okay, so this is unfortunate because what we have on the number line is a value of 1. Let's say this is 2, and I'm going to split this into thirds. 1/3, 2/3, 3/3. So 1 plus this value here is slightly less than 1/3. So that means my gap is like over here. It's like the tiniest little bit less than 1/3. And then this value is exactly 1/3. And so my gap stops exactly on that third line. So this value here on the number line is 1 and 1/3. And this value here on the number line is 1 plus 2/3. Okay, so that's bad because obviously there's no integer m that I can squish in here because my integers are over here and over here. And so that means that n cannot equal 4. n equals 4 is bad. Okay, so, and like I said, what I'm really trying to do is find a pattern. So let's do the next number. I think that would be instructive. So n equals 5. Let's see what happens. Got something over 5 less than m on 5 less than something over 5. So let's start with a third this time. I had to multiply bottom by 5 on 3. So top is 5 on 3. And so we get 1 plus 2/3. So we're already starting to see a pattern because it went from 1 plus 1/3 to 1 plus 2/3. And then on the left, what do I get? So this time, if this is equal to 33 on 100, then I need to multiply the top by 5 on 100. Now, what is 33 times 5? That should be 165 on 100. So this becomes 1 plus 65 on 100. Okay, so if we plot that on our number line and see where our gaps are. Okay, so let's draw what's going on in different colors. So this gap was for n equals 4. And then the gap that's going to be around here is going to be for n equals 5. And the gap looks like this. We've got 2/3, 1 plus 2/3 on the right. And on the left, we have 1 plus 65 on 100. And that's slightly less than 2/3 because 2/3 is bigger than 66 on 100. So 65 on 100 is even smaller than 2/3. So it looks like this. Whoops, what is happening? Okay. And something else that I want to figure out is, actually, let's do it later. So let's just do some more numbers first. So we're already seeing a bit of a pattern. It seems as if the gap shifts by 1/3 every time. So we'll do n equals 6. And so we get m on 6 on 6. Now, clearly it's going to be 2/6 is equal to 1/3. On the left, we've got to multiply by 6 on 100. So we've got 33 times 6 on 100, which is 198 on 100. And that is 1 plus 98 on 100. So you can see that this number is really close to 2, but not quite 2. And this number is exactly 2. So this goes here, whoops, on the number line. And this thing is a little bit less than 2. So it's like over there. And again, there's no integer that gets covered. So this was for n equals 6. Okay, so from this, I think I'm already just going to start to draw out a pattern. I think we have enough to understand what the pattern is. So what's the pattern between these gaps? So the pattern is that there's two things happening. The gap shifts by 1/3 as n grows, as n increases. And something we haven't actually investigated is the size of the gap. Because if the gap just shifted all the time and the gap never grew, obviously there would be no solutions. But we know that at some point the gap gets big enough to be able to very comfortably squeeze in an integer. So over here, the gap was size 2. And over here, the gap is obviously really small. Like for n equals 6, the gap was 2/100ths, because that's the difference between this left value and this right value. And then over here, what was the gap? So the gap was 2/3 minus 65 on 100. Okay, well, that's equal to, let's do common denominator, 200 on 300 minus 65 times 3 is 180 plus 15, 195 on 300. Okay, so let's just make everything common denominator. That's 6 on 300. And this is 5 on 300. Okay, so we can already see that from n equals 5 to n equals 6, the gap has already grown by 1 on 300. And I think you can guess what the gap is here. The gap is probably going to be 4 on 300 to follow the pattern, but let's check. So what's the difference between the rightmost value and the leftmost value? Well, we've got 1/3 minus 32 on 100 is the gap. And that gives us 100 on 300 minus 96 on 300, which is 4 on 300. Okay, so that means that the gap grows. So the gap is getting bigger by 1 on 300 each time. So from here to here, we plus 1 on 300 in the gap. And then from here to here, the gap has grown by another 1 on 300. Okay, so gap grows by 1 on 300 as n increases. Okay, now where should I start writing? Okay, I think I'll just write on the right here. Okay, so we've got the gap shifts and it also grows. Okay, well, there's a couple things I can notice just from these two observations. Now, if I want hope of covering an integer, remember that's the end goal. We need these blue intervals to cover an integer, because then that integer that it covers can be our selected value of m. So if I want the gap to cover an integer, then a couple things have to happen. First of all, the gap needs to be big enough, right? So let's start with the big enough condition. So we'll look at this second observation. The gap grows by 1 on 300. So you can see that if I want any hope of capturing an integer, because the rightmost value is always exactly on a third, a perfect third value, then that's never going to capture that integer because my value of m has to be less than that value here. So my value of m has to be to the left. So I'm going to focus on the left thing here. I basically need this left thing to grow big enough that I can squeeze an integer in there. So remember the two observations, I'll go over them again. The gap shifts by a third. And when I say shifts by a third, I mean that the rightmost value increases by a third each time. And when I say that the gap grows, I mean that the left moves this way. Yeah, because remember, plus a third, plus 2/3, and then, well, this is basically plus 3/3. So the rightmost value is always on a perfect third, and the leftmost value just moves ever so slightly to the left each time by 1 on 300. So if I want any hope of capturing an integer in that gap, then clearly I need my leftmost value, my leftmost part of the gap, to move to the left so much that it overlaps into the next third. So let's draw that out. I've got an integer here, k, say, and then this is k plus 1. And then if I split it into thirds, then my gaps look something like, let's say this, and then this, and then it grows a bit more when I increase n by 1. So it gets even closer to the left, and then it grows even more until finally the gap covers the next third down. So I need this situation to happen. I need the situation where the gap grows so big that I capture the next third value. That is a necessary condition. So I know that's not an integer, but at least it's a perfect third. And the integer, whether it's an integer or not, will depend on where the gap shifts. So how do I convert that into maths? How do I convert the fact that the gap needs to grow big enough? Well, that means I need my gap to be greater than size 1/3. And I'm going to write that in terms of 300ths, because I know that my gap grows by 1 on 300 each time. So if I started with a gap size of 4 on 300 when n was equal to 4, and then when n was equal to 5, I got a gap of 5 on 300, then the rule is basically that the gap is n on 300 when n, for any given n. So that means that, so this gap is achieved when n is equal to 100. And if I want my gap to be bigger than that, then I need n to be greater than 100. Okay, so this is the condition that I get from my gap being big enough. Gap is big enough. And then now let's not talk about the size of the gap, but rather the location. And so this location thing is where I can enforce that the gap covers an integer. So let's have a look on the left here at my number line thing. So this was n equals 4, n equals 5, n equals 6. If I kept on going 3, then n equals 7 would look something like this. N equals 8 would look something like this, because it shifts by a third each time. And n equals 9 would get that 3. So I think it's clear that if it shifts by 3 each time, and we want the gap to cover an integer, then since the right part of the gap falls on an integer, every time n is equal to 0 mod 3, so 9 is again 0 mod 3, and I want my gap to be big enough so that the left side covers an integer, then this value is definitely going to be 1 mod 3. So n is always going to be 1 more than a multiple of 3 if we want to cover an integer with that gap. So that means that n is equal to 1 mod 3. So these two conditions are actually absolutely necessary. So from the pattern that we've discovered, these are necessary conditions. And when I say that they're necessary, I mean that you absolutely cannot get a value, an integer value of m, when n doesn't satisfy these two conditions. So let's combine them and see what our value of n is. So let's see what the smallest n that satisfies these conditions is. Okay, so n is greater than 100 and it's 1 mod 3. So the smallest n that satisfies that is, okay, so 99 mod 3 is 0, because that's 33 times 3. That means 102 mod 3 is 0. So, 103 mod 3 is 1. So n equals 103 is the smallest one that satisfies these two. Okay, so you might think that we're done. You might think we've actually answered the question, but I actually do need to check if this works. So let's actually check if it works. I mean, from our pattern, I think we all believe that it should, but let's actually check it. So these are also sufficient, is what I was trying to say there. Like, what we discovered about the pattern is actually enough to guarantee that this should work, but let's just check it for sanity. We don't have to, but we should. Okay, so what was the original thing? The original thing was 0.33 less than m on n less than 1/3. So if I want to get a denominator of 103, then, so if this has to be equal to 1/3, then the bottom has to get multiplied by 103 so the top has to get multiplied by 103 on 3, and that is equal to 34 plus 1/3. I know that because 33 times 3 is 99, so 34 times 3 is 102. So 34 plus 1/3. And then my left-hand side has to be equal to 33 on 100, right? So to get a denominator of 103, I had to times 103 on 100. So I have to times 103 on 100 to the top. And okay, so so 33 times 103 on 100. I'm just going to say 33 times 1 plus 3 on 100, which is 33 plus 99 on 100. Yay. So as you can see, we've just made our gap. We've just made our gap big enough in order for us to be able to squeeze this integer value m in between these numbers. So the integer that lies between 34 plus 1/3 and 33 plus 99 on 100 is m equals 34. So that means if n is 103, then m is equal to 34. And that's actually the smallest. And it's the smallest by what we've just proven. It's the smallest because we saw that these conditions had to be met in order for the thing to work. And then we chose the smallest n that satisfies those two conditions. So now we've found a value that works and we know exactly why it's the absolute smallest. So yeah, as you can see, you didn't have to go even to 300. It was even smaller than 300 and it was way smaller than 600. Okay, any questions? Were there no questions for that?